Mathematics is a story, and like any good story, it evolves. So, please take this lecture as an entertainment lecture. I request that TS no questions should be asked from this part of the discussion, because when you take a long journey, sometimes you have to have some entertainment. So, these are entertainment, you can forget your books, etc., everything. After the Riemann integral became famous, it was later gradually realized there were several functions which are not Riemann integrable. In fact, Riemann's PhD supervisor gave an example, which is now known as the Dirichlet function, which we have written fx is equal to 1 when x is rational, is equal to 0 when x is irrational. So, you are asking, do you have a Riemann integral, is Riemann integral between 0 to 1? Answer is no, of course, we have done that. So, but that is that a deterrent, in the sense that can all these functions which are now rejected by this Riemann integral theory as integrable, are they integrable in some sense? Because we are no longer looking like Newton or Leibniz as the integral as an area. We are thinking of integral as a number calculated in such a way as a limit of sums, limit of some telescoping sums. So, then in 1902 there was this famous thesis of Henri Lebesgue from Paris. And which he did a very different thing, which he said, okay, what would happen if you have a function, does not matter, maybe bounded function or whatever, nice function, from A to B, they say, okay, instead of partitioning the, there is a bounded function, so there is a range, instead of partitioning the x axis, I will partition the range. Instead of partitioning the domain, I partition the range. So, let us see if I partition the range, what would happen? Say it is y0, ya, yb, fab basically. So, maybe I will put some points here. But again, if I have to calculate the area, I have to construct the rectangles here. So, idea is this, that let me see, if I take this partition of y, what are the corresponding x's that are coming in here? Suppose the function is like this, then in this range of values in y, this part of x's are also coming in. So, if you want to construct the rectangles now on the x's, so corresponding to this, you have to now you will now corresponding to this y parts, you will be taking the corresponding x parts which corresponds to these y partitions, and then take the function, some functional value in this, and then take the. Now here, so you want so what you will do, you will choose a functional value from here. Understand it. This is a very interesting thing. So you will these are the y values. So you will choose the functional values from here. Okay, you will choose a functional value from here. So this value, look at this point. So look at this point. This value corresponds to, this is the point. So it corresponds to this x and it corresponds to this x here. So, but the partition corresponds to this part and this part. So, if you want to make the sum now, you have to multiply the value of this function, functional value, take this particular value, and then you have to multiply by this some sort of a length of these two sets. Okay, I will just rework it out. So, let us just see what Henry Lebesgue has done and how this nice idea came about of measure. It could be for very bad looking functions also. So, maybe I will just do it for nice looking functions so that you do not have much. So, or maybe I will just do it. So, here is my range YA, YB. So, this is FB equal to YB and FA equal to YA. Okay. But my range is not really YA, range actually goes from the minimum point. So, this is the minimum value. So, but this is my YA, right. So, this is a FA is YA. So, this is my starting point of the range, which is my Y0, and stopping at YB and YA is in between. So, what happens? So, I now partition this into small parts. Now, if I want to see where the x's of this partition lie, this particular first partition. So, you see here this is one point, this is one point where all the corresponding to this x, the partition value is lying this point. So, this is the corresponding x's on the x axis on which it is lying. Okay. Similarly, if I take the next partition point, so let me tag it, let me just push it through. So, what happens here? What are the values which are lying? Here the values which are lying in this partition is this part, and then up to the and this range of x. So, for this part of x, function values are lying within this second partition. So, I am partitioning the range, I am not partitioning. So, this is my second range partition, I am partitioning the y axis. So, what the idea is, so this is a partition of the y axis. So, now I am seeing this is the x part for the first partition. For the first partition, this is my x part. For the second partition, this is my x part. So, they are not just one interval, they are basically a union of two intervals. Now, what I will do, how I will form the sum, or the Riemann sum if you want to call it. So, I will take some point here and I will take some point here. So, which are the tags on the partition. So, I will just see where this point lies. So, point lies here, okay, this is the x, it also lies here, does not matter. So, then for this also for the first one I choose some y value which is a functional value, and for the second also I choose a y value which is a functional value, and with those values what I have to do? I have to multiply the length of the interval. But for the second case, where is my interval? I have two union of two intervals. So, you can say, okay, why do not you write the f dash xi into the union of two intervals, but that is not my wish. My wish is to have a function value and into one interval. So, but then what is that interval? What is the difference between these 2 points xi minus 1? That is the length of interval. So, how do I call this union of these two things as an interval? It is essentially a set, and now I do not know how will I define a length of this set. Will I call this as the union of the two intervals as the length? Shall I tell this length plus this length into the function value, which might make sense. So, essentially here, because the function is nice and continuous, you are getting such union of things, but if you have functions like this, very bad staircase functions, then things might look very bad when you partition the y axis. So, I have to now so I can get very strange kind of sets. So, for a given partition of y, so if I take an interval of partition on the range, the corresponding x's might form a set which is very so strange. So, there would not be any particular way to define its length. So, then Lebesgue thought the length is what? It is a measure, some kind of a measure of the space occupied by the line. So, can the next natural question. So, what I get is, given a partition y is in the partition of the range, so corresponding to y there are certain x's for which fx would be in that partition. So, basically what are these? I am finding the x's for which fx would be in this partition. Okay. So, what is happening is that those sets, the set A in the interval AB, the subset of interval AB for which fx is in some partition. So, I want to multiply a some value of, so take some fx value from here and multiply with the length of ASA. But if the set is so strange, set could be strange enough that you will not be able to find its length, you will not, there will be no meaningful way to talk about its length. So, how will you talk about the length of such a set? So, he started thinking about the general notion of measuring a set on a real line, and that gave rise to the notion of measure of a set on R, and which finally blossomed into a very important theory called measure theory. So, he found that once he did this, he could actually integrate functions which are not integrable in the Riemann sense. But this idea of measure of sets became very important, because there were in lot of cases we really have to measure. When we come to 2 dimension, of course, measure of a set is the measure its area, if the set is nice looking. If it is not, how do we think about it? So, then he said that based on the idea of the length of a line, he said that the measure must satisfy certain properties, and he listed those properties which are the axioms of measure, and any function which satisfies, when acted on a set, satisfies all those properties, can be termed as a measure of that set. And now what you are basically doing, what you do now, how the sum will be done, function value into measure of the set for those x's for which fx would be in the same partition as this function value, this y value. So, you will have some y dash from some y1 from the first partition, y2 from the second partition, multiplied with the measure of the set, so that all the x's in that set has the function values in the partition in which y1 is contained, right. So, that is the idea. So, the sum in this case would be for y into measure of a1 plus y2 into measure of a2, and so on and so forth up to yn say. So, yn is one element from this set, but measure a1 is a set such that for all x, fx here, fx lies in the partition in which y1 lies. So, this whole game has now changed. So, he had to do the same sort of summing, same sort of idea of rectangle building, but coming from a very different perspective allows you to build new mathematics, and that gave rise to measure theory and integral, which was effective enough for many things. So, it became the official integral. So, poor Riemann got left out. So, Riemann is still troubling many mathematicians' lives with his Riemann's hypothesis, but the question then came, measure is a concept not so easily understood, is a concept not so easily handleable, is a concept which is very not so easy to digest, because we have some very fair notions of geometrical idea of measure of sets or objects which are already ingrained in our mind. To think of measure as an abstract concept, as a function which satisfies certain axioms or properties, is something not so easy as one might think. Many mathematicians who use measure theory might say, oh, what is the problem? It's just like that. You are again getting used to things in mathematics. When you get used to things in mathematics, these things won't look problematic. But if you are not used to those things, but you want to look at them and try to see whether it is easier than what you have read. For example, in the Riemann case, measure theory would be slightly hard nut to crack compared to the way you have been fed with Riemann stuff. Coming from Newton to Riemann was not a very difficult thing. It was the same game done in slightly different way, and he enlarged the class of functions from continuous to bounded. But here he does something much more different, that I enlarge the class of functions which Riemann could not even handle. But to do that, his tools very strongly deviated from which Riemann had taken. It is not the standard path. This question was addressed by these two mathematicians, one a Polish mathematician and one a English mathematician. Kurzweil, I think the name will immediately tell you, is Polish, and henstock is an English mathematician, who in the 1960s spoke about, asked this question: what Riemann did was an extension of Newton's idea, which is a very clear idea what is the meaning of integral, first as an area and then trying to extend it. See, if you have seen, we are making a very nice historical development of the integration theory. Now, so they ask the question, can't Riemann's approach be modified without getting into this measured theoretic approach? See, measured theory is a huge deviation from what you have known. So, can't the Riemann's idea be modified? So, see, when you came from Newton to Riemann, it did not bother you. Okay, same partitioning the interval, constructing sort of rectangles in their mind, and okay, instead of constructing rectangles, he is doing the same thing, but he is not telling it. If the function value is non-negative, he is the same thing as what Newton was doing. Okay, Newton did not understand much about bounded functions, they did not bother, they were only looking at continuous curves, fine. So it is not a very difficult thing to accept, okay, fine. Riemann was a genius, we aren't, he caught it, we did not, that is all. But the case is very different when it comes to Lebesgue. To think like this is not so easy, because your integration theory is linked with the notion of area, that this whole notion of area and building rectangles is so ingrained into our mind, nobody will ever think that you can also partition the y axis, the range, and that is why, to make this break from the traditional thinking, Henry Lebesgue would always be a giant of 20th century mathematics in general. But these two mathematicians, much less well known, asked a very pertinent question. You can say, okay, these guys were just asking questions from an educational point of view. Not really, because that is a pertinent question, that can my basic geometric intuition remain when I want to broaden the idea of the integral, broaden the class of integration? Can my basic geometrical idea which Newton had propounded, can that remain? Because that is the idea with which Riemann started. So, the question is, can Riemann's approach be modified? And that is what these two people have done. There are several books written and several mathematicians are trying to push this integral. Maybe one day it will also be one of the accepted official integrals in mathematical community along with Lebesgue integral. So, we are not going to discuss Lebesgue integral because it needs tools which are not for this course. What we are going to do, I am just going to show you just I have two in my own collection I have two books. I do not even ask you to go and read these books, but just for the namesake which books I had followed. One is Modern Theory of Integration by Robert Bartle. He is very famous. He has a very famous teacher and has a very good book on analysis, mathematical analysis. And this is it's a lecture notes called by the Australian Mathematical Society, lecture series number 14, the integral and easy approach after Kurzweil and henstock. So, we will just follow what is from here. This would be slightly more technical for you, but we will try to follow what is in here, and we will try to define this henstock integral, and then we will try to show that one integral which is not one function which is not Riemann integrable is integrable in this sense. So, what he does, so let us go back to the Riemann integrable and rethink, not in terms of upper sum and lower sum. It is actually this Darboux approach that we take that confuses us. Newton did not take the Darboux approach, he took that sum and then take the limit. Riemann did the same thing. Darboux actually played a little spoil sport. He made this easy LPF, UPF and everything got jumbled. So they want to go back to that same limit taking business. Make the sum, take the limit, right. So what you do in a, so this is a partition P. So if I write this as x1 and this is, so x1, x2, x3, xn minus 1. So I can start with indexing, right. I can start with xi1 as one element I choose from here, xi2 I choose from here, xi3 I choose from here, xin I choose from here, and so on. Once I do tag some points there, tagging is something you know it very well in the age of Facebook. I do not have to tell you what is tagging. You are tagging photographs day in and day out. So when you tag a point here, so this is called a tagged partition. So tagged partition is usually given like this. A tagged partition is always expressed in this form. This is a tagged partition. So the partition element and the tag. Now what did Riemann do? Sorry, I made a mistake. Thank you for pointing. X is xi minus 1, xi, right. So this is a partition, this is a tag partition. So P dot is the sign which many people use and he is also using, which is standard. So what did Riemann actually do? What is the Riemann sum? The Riemann sum now what you want to do? You want to show that it is less than, so there is a number which you will call an integral between a to b if the difference between this and that number can be made as small as possible. But how do you get to that number? You go by definition of Riemann, you get to that number by increasing the number of n's. So once you increasing the number of n's, that is partition points, the length of the intervals become smaller and smaller. So, given a delta, you can always have a partition so that each of the intervals have a length less than delta, 2 delta, right. So, given an interval, given a tagged partition, right, like this, xi I, xi minus 1. So, I can have a delta such that you have here xi I plus delta and here you have xi I minus delta and xi I minus delta to xi I plus delta. This actually contains this interval xi minus 1 xi. You can always do that. Once the points increase, given a delta, you can increase your points in such a way that you can always get this. If you can do that, then such a partition is called a delta fine partition. So you can, so if you can always do that, this would imply that the partition is delta fine. What is the meaning of partition with delta fine? The largest length of the largest interval is less than 2 delta. That is simply this. This is a big name given to a very simple thing. The mathematicians are very capable of doing such things. So, essentially you are controlling this. So, what is a Riemann integral? Riemann integral simply means that given any epsilon greater than 0, given any we can find a delta greater than 0 such that for any p dot on a tag partition which is delta fine, we have this is the definition of the limit actually. That limiting definition is written in terms of this delta fine partition. This is less than epsilon. Now, this delta is now a fixed positive quantity. What if I could control this delta? What if I could change this delta for every epsilon? Then I could take out some superfluous point which are not many of them, but at which the function values are peaking and not allowing us to control the distance. Such is a case where the notion of gauges were introduced by henstock and Kurzweil very separately. So, I will do it. I do not have time to actually give you an example of why you need to talk about gauges, but I will show you when we do that particular example. So, they defined what is called a gauge. So, what is a gauge? Gauge is nothing but a function from AB to R plus such that for any, this xi is always need not be exactly in the middle. Xi could be a xi could be this x1 could be also a xi, which could be the tag for both the partition, both this one and this one. It could be xi1 and xi2 both. That can also happen. A0 could be the tag also. A could be the tag. So that for any t element of AB, actually I should write it directly R plus plus R, or just write R into R such that for any t element of AB delta t is strictly bigger than 0. So for each tag point now I will have a separate delta. Here what is the meaning of delta fine? A single delta should work for all the, here I am saying okay I do not need a single delta to work for everything. I will need just a gauge I will use, for everything it will change. So, just a little bit of thought process. So, now we will define in the same way. So, if you have an interval say x I minus 1 to x I, and if you have a xi. So, what is that interval which is controlled by the gauge? So, the gauge is that's controlling that interval is you can keep it as open interval, you can keep it as a closed interval, does not matter, it is up to you. These guys have taken it as an open interval, closed interval, but I sometimes prefer to put it as an open interval, it does not matter. So, this is your controlling interval, right, and it should be, so this interval x I minus 1 x I should be inside it. Actually what it is telling, that every interval would be controlled differently. Here every interval is controlled in the same way, there every interval would be controlled in a different way. So, this is a very key feature of the gauge which is not there with other things, right. So, but how do you know that if I give you a closed interval a b, right, which is non-degenerate, a is not equal to b, whether such a gauge exists, whether you will be able to for every tag construct such an interval. So, for every tag that you have, says II here, so is II. So, every interval that you have which is tagged, for every tag, now the whole interval is tagged, we are only talking about tagged partitions. So, given an interval AB, how do you know that there will be a function such that for whatever be your tag partition, you can always use that xi I value and control the, and so that this interval will actually contain this interval. Basically this open interval essentially would contain this interval, does not matter, open or closed is not a big issue. So, this thing is that, is there a gauge for which I can do it for any xi. So, with this, now what is here, delta is not just a fixed number, the number can change, but the functional form is same. So, there is a function, that functional form is same for every tag that you use, but only for every tag the xi, the del xi value changes. Can there be a tag given a closed a compact interval, this closed and bounded interval, a closed interval, is there a tag, is there a gauge which through which I can do this thing, this controlling of the intervals? The answer is yes, and that is done, given by a Belgian mathematician called Cousin. They would call Cousin, but we Indians know this spelling and we will call it Cousin. It is called Cousin's lemma. Actually, using Cousin's lemma you can prove other things, you can prove even many other issues like extreme, you can prove that okay, a function bounded on an interval as lower bound, upper bound, all those things can be proved using this. So, here if I have an interval I and I have a gauge for which for every subinterval of the partition, of the tag partition, I have this feature, then I call that sort of partition is that this is delta fine with respect to the gauge. So, now Cousin's lemma said that if I define a function delta on, if I define a function delta on the interval AB, the delta is a function from this which satisfies this, that is delta is a function from AB to R plus plus actually, then there is a partition I of AB which is delta fine. There will always exist a partition I which is delta fine. So, actually my earlier statement should be, I made a little mistake, it should be written given an interval AB, a delta fine gauge exists, a gauge exists which is delta fine, a gauge exists which makes a partition delta fine. So, given a gauge on AB there exists a partition I which is delta fine. So, here delta is no longer a number, it is a function, delta fine with respect to the gauge. Now, how are you going to define? So basically you have to show the existence of a partition which is delta fine. So, given a gauge there is always a delta fine partition. Obviously, the next question would be, which would be natural, that of course you can ask that given any partition I, the question is there a gauge with respect to which it is delta fine? That is a question. That is if I have a partition, a tagged partition, is there a gauge can I define a gauge with respect to which is delta fine? It is obvious because you can always define the constant gauge. But given a gauge which is not constant, the more relevant question which Cousin's lemma answers is that can you have a partition which is delta fine with respect to this gauge, not a number, right. So, now we are going to define the KH integral. For those who want, I can just show you the pictures of those two mathematicians, at least from the book maybe you would understand something. Maybe I can just put forward, I do not know whether how much visible it is to you, but maybe they can zoom in the camera and they can show you something. So, here are the two mathematicians, here is the English one, henstock, you can understand, and here is the Polish one, Kurzweil. So, henstock and Kurzweil. So, here we define the integration and then we give an example and finish our discussion. So, our major discussion of integration is over. Next are just applications, where we show some techniques of how to integrate, some ideas of improper integral, some other applications, calculating volumes, areas, surface area and all those things, and then into other issues of analysis. So, here I would just write down the definition from Bartle. So, you see now I have extended the idea of the Riemann integral just by taking his approach, slightly modifying it, but it is not very hard to understand. So, the definition is from Bartle, modern theory of integration. A function f, say from AB to R, is called KH integrable or generalized Riemann integrable, is called KH integrable if there exists a number A element of R such that for every epsilon greater than 0 there exists a gauge delta E. So, this gauge would depend on the choice of your epsilon. So, that is something very important. Such that for any tagged partition, so there will be obviously a delta fine tagged partition by Cousin's lemma. So there can be infinite delta fine tagged partition, there will be actually. So if one prove one, you can do the other. So for any tagged partition P tilde P dot sorry is a so that for any tagged partition P which is delta fine. So delta fine essentially means this, for every interval this should happen. So the length of interval should be less than twice of delta. So which is delta epsilon fine, we have summation I is equal to 1 to n say sorry n f xi I xi minus xi minus 1 minus a. So this is the definition. There is some mistake here, this is minus. So basically you have here these two endpoints. Yeah, thank you. So this is xi plus delta epsilon I, and this is xi, this one is xi minus delta epsilon I. So those who have copied it as plus, obviously it will not make sense because this would be of length 0. So this is an obvious typographical error, writing error basically. So this is this interval should contain this interval. So length of this interval should be less than twice of delta epsilon I. So that is the meaning of this. So there is the definition. So we recast the same definition of Riemann now with this. So here there is no upper sum lower sum business. I can't think of any upper sum lower sum description of this thing because that will again take away the delta fineness, that control that you want to have, that control will go. Maybe there is, you can actually devise some upper sum lower sum theory. I do not know, maybe one has to think about it, but it is not really required. So now what I am going to do is to go give you this example and end, the famous Dirichlet example which Riemann could not prove that it is Riemann integrable, it is not. So here is the one that is integrable now in terms of this kh integral. So it took the Polish and English brain to outwit the German, at least in this integration business. So here is this Dirichlet function. When x is rational, 0 when x is not rational, besides x is irrational obviously. So what do? You take a partition, right. Now in the interval 0 1, so f in this case is defined from 0 1 to r. So now in the interval 0 1, so we are trying to seek what is the meaning of fx dx in the Kurzweil sense. Now in the interval 0 1, you know that as the rational numbers are countable, you can line the rational numbers up as r1, r2, r3, r4, r5, whatever. So when you tag, so in your taggings, So, some cases the tag would be a rational number, some cases the tag would be irrational number. So, of course, one can say why you do not I just take a partitions in such a way and that I will only tag the rational numbers, where every partition will have a rational numbers. Why I only a finite number of, so I only tag the rational numbers. That is also one way, but a more general way is that you have a partition, you just tag arbitrarily, it could be rational, it could be irrational. Okay? So you have this and the rational numbers are there. So, they could be enumerated, right. So, Rk is the enumeration of rational numbers, is the enumeration of rational numbers, of rationals. Okay. So, you know that this is not Riemann integrable. So, now you define a gauge functional on 0 1 to R in this way. See, you know, whenever there will be, when you tag a irrational, the functional value would be there 0. So, that interval is useless, whether you control it, you do not control it is of no meaning, only the rational one has to be controlled. So, you define this as the following. So, xi by 2k plus 1 if t is equal to rk. So, t will be some k, na? T will be some rational number which is R1 or could be R1, could be R3 or could be R4, right. So, you go on like this. So, you start from 0, t, d0, d1 and then they go on. So, whenever you get a rational number, if it is R1, so it is 1 by 2 square, basically GP series, nothing else. You need a convergence somewhere. So, and for the irrational case, it does not matter what you put, you just can put a constant, because you do not need to control it, it will be 0, it will have no effect on the sum. So, put 1 if t is irrational, t is in the complement of q which is irrational. So, I am hoping that this definition is already done. So, we can now actually work this out. So, let us look at the sum. I equal to 1 to n. Okay. Now, let us consider any, so there must be a partition which is delta fine. So, let us take a partition of n points which is delta fine. Now, let P be a delta fine, delta epsilon fine partition of 0 1, of 0 1 which has n points, does not matter. So, let us look at this thing, right. Let us look at this. So, only contribution is coming from rationals and that would be less than equal to summation whatever be the number of rationals I face. So, it will be less equal to k equal to what? Infinity to the cardinality of rationals, or I need not write, say I have faced, say I could face say p number of rationals out of n tagging, say p less than n, right, p strictly less than p number of rationals, p could be equal to n, could be less than n. This I will definitely have, right. This sure?
It's n plus 1 also. N points partition. Maximum you can have.
N point, no, first part thing is given as xi 1, xi 2, xi n. First x0 to x1 the tag is xi 1. So, last one the tag is xi n. So, no, I am telling it could be n, p is less than n, because some tag could be irrational. So, irrational things do not matter, rational things matter, right. So, why did not I take rationals at the very beginning? I might not have a partition which is tagged all by rationals, which is delta fine. So, if there is a delta fine partition which has no rationals, then it is obvious 0, finished. If it is tagged by some rationals, it is still less than this, where p is strictly less than n. But this is again less than, so what you will have? So, I equal to 1 to n f xi I xi minus 1 xi by 2k plus 1. This is strictly less than, sorry, k equal to 1 to infinity xi by. Now, if you go by this thing, this will become 1 in the GP series. So, k equal to 1 to whatever. So, this will become, so this will be equal to epsilon. So, half, right, epsilon by 2. So, it starts with 1, right, half plus half into 1 plus 1, so that would be 1, so it is half. So, epsilon by 2. So, that is my chosen epsilon. So, what is my number here? It is 0, because this is this minus 0. So, for any delta fine partition, any partition which is delta fine, that is controlled by this delta, I can show this. So, it implies now in this sense and that is it, job done. So, I hope you enjoyed this entertainment lecture where we successfully integrated something which was not Riemann integrable without using the measured theoretic approach, but using the simple extension of Riemann's idea. Thank you very much.